right, hello everyone, and this is Mrs. Price. I'm trying something new. I am trying to use my Chromebook and a stylus in order to do this lesson. I don't know if I can get this off the screen. There we go. So this is going to be section 6.1, which is on polynomials. And today we're going to just kind of learn the basics of what a polynomial is and a little bit about graphs and factoring and the different types of polynomials. Here we go. So first thing we're going to talk about are, you might already know some polynomials. So in the table below, which I'm going to fill out for you, we're going to talk about the number of terms, the degree, and the type of the polynomial that it is. So this first one, which is just the letter C, traditionally in math, C represents just a constant. There is only one term. Let me move this up and get to, there we go. One term. The degree is 0, and we'll talk about, so the term, each of these that are separated by a plus sign are called terms. So each of those items would be a term. The degree is the highest exponent that is on the variable. Since there are no variables in this first one, the degree would be 0, and we would call this a constant function. For the next type of polynomial, we do have a variable. There's still only one term, but now since you don't see an exponent, we think of it as an invisible 1. This is k times x to the first, so the degree is 1. And this type of function would be called linear. This next one, very similar to the last one, it's still a first degree function, but there are now 2 terms, and it's still linear. This next type of function has 3 terms, and because the highest exponent is 2, the degree is 2, we would call this quadratic. We could also call it a trinomial because there are 3 terms. So the next one, we have 1, 2, 3, 4 terms. The highest exponent is 3 because we have an x cubed, and we call this a cubic. And the last function, we have 1, 2, 3, 4, 5 terms, and the highest exponent is a 4, and we would call this a quartic. All right, so those might be some functions you already know. If we had an x to the 5th, it'd be a quintic, and so forth. All right. So the first type of function, which you should be very, very familiar with, is a linear function. And so what we have here is we have some points plotted. And what you notice about linear functions is that as x moves forward by 1 place, your y value needs to form what's called an arithmetic sequence. In other words, if we were to subtract each of these terms, you get the same value every time, right? So that value is the common, we call it the common difference. It's also called the slope. And if you think about it, what are we doing to get from one point to the next? We are going up 3 over 1, up 3 over 1. The next point, up 3 over 1, up 3 over 1. And you continue this little, same pattern all the way through. Even though the scales are different, it looks like we're going up less than we're going over. But if you look at your scales, the x's are going by 1s and the y's are going by 5s, so it's a different scale. So anyway, so we're going up 3 over 1. Our slope is 3. If we wanted to actually find a linear model for this data, let's see, how can I move my screen up? I'm trying to think here. I'm going to go to select, see if I can figure out how to add more space. I don't know if I can. All right, so I can't raise this up and add more space. All I can do is move things around, but what I can do is add a blank page. So what we're going to do is kind of go back and forth a little bit, and I'm going to show you that since our slope was 3, and we know then that if we were to do something like a point slope form, then our m, our slope, would be 3. And if I go back to the page I was just on, all I need is any point. So I'm going to use the point 2, 10, and go here and say y minus 10 equals 3 times x minus 2. And this would be a perfectly good equation for this linear model. Now, if we want to clean it up, solve it for y, we could say y minus 10 equals 3x minus 6, and then add 10 to both sides, and you got y equals 3x plus 4, and that would be our linear model for that data. However, most of the polynomials we're going to deal with in this chapter are not going to be linear. They're going to be a higher degree. So linear functions have what's called a common difference or a constant slope between consecutive y values. However, nonlinear functions also have patterns that we can find inside of them. But the first thing we're going to do is talk about what is a polynomial. A polynomial, first of all, notice one variable. Now, it's okay if you have a y equals, that's okay. X would just one, what it really should say is one input variable. So a polynomial has one input variable, and then it can be written in this manner. Now, it looks a little confusing with this a sub n x to the n, a sub n minus 1, x to the n minus 1, but the a's just represent the coefficients. So when you have these a's in front of your x's, those are just numbers. They just represent different numbers. So the a sub n means the nth a with x to the nth power. And then a sub n minus 1 would be the next coefficient with x to the next power, and so forth. So x is your variable. The exponents on your variables must be non-negative integers. That's really important. You can't have x to the 1/2. You can't have x to the -3rd. It can only be non-negative integers. Coefficients are all real numbers, and your final coefficient can't be 0. If it was 0, then it wouldn't be an x to the nth polynomial. All right, and then each monomial that is separated by a plus sign, that is called a term, which we're already familiar with. So here's another example of some polynomials. So a sub n x to the n, that means that the fourth coefficient for the coefficient of our x to the fourth term is 5. And then our next coefficient would be -2 for our x cubed term, and then 1 for our x squared, -3 for our x to the first, and 3 as our what we call our constant term. All right, and then this is just a repeat of what we did when we did it the opener. So we have a constant function has a degree 0, and it's just a number. Linear function has a degree of 1. Remember, what is degree? Highest exponent on the variable. So the degree of this function, since it's an x to the first, would just be a first degree linear function. And there's an example. Highest exponent on this function is 2. It's quadratic, and there's an example. Then third degree function would be a cubic. Highest exponent is a 3. And then fourth degree, highest exponent is a 4. It's called a quartic. Notice on these examples, you don't have to have all of the terms in between. Like this example here, there's no x cubed term, there's no x squared term. That's okay. If some of your middle coefficients are 0, that's okay. That's fine. All right, there are two things that will cause a function to not be a polynomial. So to not be a polynomial, we're looking for negative exponents and fraction exponents, or Another way to have a problem is if the exponent is a variable. So let's take a look at this first function and see if it's a polynomial. So we have x to the fourth, that's fine. Pi times x to the cube, that's fine. Negative 5x squared is fine. And plus 1 is fine. All of our coefficients are real numbers. They don't have to be rational. That's okay. They just have to be real. So pi is fine. And all of our exponents are integers, positive integers. Remember that this one is an x to the 0. That's okay. So yes, this one's a polynomial. This next one would be a no. Why is it not a polynomial? Because we have a negative exponent. When you have a negative exponent, the function is not a polynomial. The next one, we have positive exponent, positive exponent, positive exponent, all real coefficients. Yes, this one is fine. The next one, we have a problem. Take a look. Do you see the problem? It's right here. We have an exponent that's a variable. That is bad. You can't have an exponent that's a variable. That causes it not to be a polynomial. It's still a function, it's just not a polynomial. This last one is also, pretend that's kind of connected there. This last one is also not a polynomial.
Please call 58021.
And the reason it's not a polynomial is because of this root x. When you have a root, any x inside of any kind of a root, a square root, a cube root, any root, that actually causes your exponent to become a fraction, and that means that it is not a polynomial. So this would not be a polynomial. All right, we're going to learn how to figure out the degree of the polynomial by subtracting subsequent y values. So if our x values are separated by 1, then if our y values as we subtract, so 13 minus 10, 16 minus 13, 19 minus 16, if we get the same number every time, then the polynomial ends up being a first degree polynomial, which means, of course, we would call it linear. All right, we're going to learn how to find some higher degree polynomials using what's called the finite differences method, which is kind of fun. I think you'll like it. All right, so suppose if we go from, now the x's don't have to go by ones. If you notice here, they're not going by ones, they're going by 0.1. As long as these are evenly spaced, it's fine. They don't have to be by 1, they just have to be evenly spaced. If your first differences are the same, it's linear. But if they're not, you find all of your first differences, so you just subtract. 2.88 minus 1.88 is 1. 3.92 minus 2.88 is 1.04. And you go through and you find all of your differences. If they're different, you know it's not linear, so then you find the differences of the differences. And if the differences of the differences are the same, so 1.04 minus 1 should be, that's interesting, should be 0.04. This is wrong. Let's clean these up. Should be 0.04. 1.08 minus 1.04, 0.04. This one, 0.04, 0.04. As long as these are all the same, then it's a second degree polynomial. Second degree, which would make it, of course, quadratic. The next one, we subtract, we get our, again, evenly spaced. So we have 52.5, 2.5, 27.5, and we just keep subtracting. Remember, you're going it's this minus this. You go this way. So from the higher term minus the lower term. Next term minus the previous term. And as long as these are evenly spaced, right? They don't have to be by 1. They could just be evenly spaced. I'm trying to draw a happy face and it's not going well. Yay, there we go. Okay, so now I've got these differences. So now we're going to subtract these. 2.5 minus 52.5 is negative 50. 27.5 minus 2.5 is 25. Then we have 100. Then we have 175. So our D1s were not the same. Our D2s are not the same. Let's subtract again and find D3. 25 minus negative 50 is 75. 100 minus 25 is 75. 175 minus 100 is 75. Why? If you keep going, they're all going to be the same. That means this is a cubic. Cubic. Third degree is a cubic. All right, and then there's just some examples of graphs. So quadratic, you already know, shape is a parabola. Cubic looks like this. Okay, so we're going to do a little experiment here. We're going to find a polynomial function that models a relationship between the number of sides and the number of diagonals of a convex polygon. So if we start with a number of sides, I had this covered up, and one of the things with this online suite is that it takes your shades away, and that's, so you'll just have to see it. So what we're talking about, if we have a triangle, there's no way to draw any diagonals to go from any vertex to any other vertex. You're just following along an edge, so, or a side of the triangle. So there's no diagonals there. But if we have a quadrilateral, then we have one diagonal this way, one diagonal this way, so we end up with two diagonals. If we have a pentagon, 1, 2, 3, 4, 5. Diagonals are just connecting all the vertices to all the other vertices if you're not traveling along a side or an edge. All right, and if we were to keep going, I mean, we could do a hexagon. And this will be the last one we'll do. So we'll start with this vertex. So 1, 2, 3. I'll go to this vertex. 4, 5, 6. And then this vertex, we've already gone here. So 7, 8. And then this last vertex, the only one left that's not drawn is this one right there, 9. It's kind of messy. Well, I'll show you 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's our 9 diagonals. All right. So what are we going to do with these diagonals? We are going to see if we can find a polynomial that represents those data points. So we're going to take 3 points from the table. So a 4-sided polygon had 2 diagonals, 6 had 9, 8 had 20. We're going to set up a system of 3 equations with 3 variables. I know I'm going to run out of space, and I'm pretty sure my next slide, doesn't have it, so I will just have to add slides when we continue. First thing we're going to do is go ahead and remember that each of these coordinates represents an x and a y. So I could write 2 equals a times 4 squared plus b times 4 plus c. For the next one, so this is my x, this is my y, 9 equals a times 6 squared plus b times 6 plus c. And my last one, 20 equals a times 8 squared plus b times 8 plus c. So we have 1, 2, 3 equations and 1, 2, 3 unknowns, a, b, and c. So I'm going to rewrite this on the next screen so I have a little more space to solve these. So blank page. So here's what we have. So we have 2 equals 16x squared plus 4. Whoops. Let's erase. Make sure I'm using the right letters here. Okay. 16a plus 4b plus c. I'm going to back up and look at my next point. Then 36a plus 6b plus c. So 9 equals 36a plus 6b plus c. And my last data point was 20 and 8. So I have 20 equals 64a plus 8b plus c. All right, so now we could easily multiply this middle equation times -1. So if I take my top equation and multiply my middle by -1 and add them down, So I end up with negative 7 equals negative 20a minus 2b. So now that's my first set. I eliminated the c's using these first two equations. Now I'm going to do the same thing using the middle and the bottom. So if I rewrite this negative 1 middle down here, negative 9 equals negative 36a minus 6b minus c, and I add my middle and my bottom together, I get 11. Let's see, 64 minus 36, so third 28, if I did my math right, hopefully I did, plus 2b. All right. Okay, so now I've got, oh, look at how nice. It's like we planned it this way. So now I've got this guy and this guy. So I'm going to just write them one over the other. Negative 7 equals negative 20a minus 2b. Add straight down. 4 equals 8a. So then we can divide by 8. And I get a equals 1/2. Now I'm going to take my 1/2. Oops, there's it. It's a. Substitute it in for a, so I get 11 equals 28 times 1/2 plus 2b. 14 plus 2b. Subtract the 14, and I get b equals negative 3/2. Then I go to any of my original equations. So I'm going to do 2 equals 16 times 1/2 plus 4 times negative 3/2 plus c. And I'm running out of space, but we can do this. I'm going to move this up here. Try and write small. So 2 equals 8 minus 6 plus c. Okay. So I get 2 equals 2 plus c. Whoa, look at that. That means c is 0. So our final equation would be 1/2 x squared minus 3/2 x plus 0. Remember that a, b, and c were the coefficients. I'm going to write that. Let's see here, up here. So we had y equals ax squared plus bx plus c. That was what we were trying to find. So when we found our a, our b, and our c, that's how we end up with the coefficients for our polynomial. And that's it. Stop.